All right. Let's see. Oh, hey, YouTube says it works. Does YouTube say it works? All right. Hello, everyone. Why does it show? Let's see. Alright, we might be live. Is anybody in chat? Is there audio? Does the stream work? I kinda don't want to start the stream before somebody says that it's all good. Alright. Interesting, YouTube shows like 0 watching people, although there's clearly people in the chat. Alright, whatever. Let's just pretend it works. I think it should be good. Alright. So, hello everyone. This is the continuation of the stream that we had on Sunday. On Sunday my keyboard broke and we planned to write code and we did not write much code. I got a new keyboard. It seems to work. I've been using this for the last 3 minutes, so hopefully I can get used to this while we're on stream, but it seems to have the same layout that I usually use, so it should be fine. So a brief refresher, we went over some of this stuff last time, and we are working on the meshoptimizer library. That's my open source project, and we are trying to improve the way how edge collapses work, specifically for situations where there is multiple UV sets. And let's see if this still works. So this is the same code that we had last time with no changes to the code. What was I testing this on? This? Right. So specifically what we are trying to deal with is there is these cases where the simplifier seems to be confused, where it's collapsing edges that should not be collapsed, and it results in these weird color shifts. This is showing UV coordinates, but the same problem can happen for any attribute. And this is what we'll be trying to deal with today. And so I went over how we are gonna do this a bit on last stream. We are gonna try to track the relationship between vertices, where if these vertices are on a seam, so there's 2 copies of each vertex, the orange one and the green one, we'll try to sort of match the green ones to the green ones, so that there's a link here and there's a link in the orange vertices, so that when we collapse the edge between 2 vertices, we can say, okay, these used to belong to the same edge and the edge was a seam edge, so we should collapse this or not. On the last stream, somebody mentioned the paper. The paper Seamless, Simulation, Similar Decoupling of Shape from Mesh Resolution. So I have read this paper before, but I forgot about this. And then after the last stream, I had a chance to read this paper again, or really skim through this paper. And this is kind of on topic if you want more sort of deep information into how, like, what are we trying to do today and how to go like one step beyond. This is a good paper to read. It seems to be pretty readable as far as papers go, you know, and specifically also it has a lot of large images and they take a while to render. So specifically in the part 5 that talks about decimation, they list the criteria and conditions for collapsible edges, and this is exactly what we are trying to do. So they mentioned these link conditions, and this is kind of what we want to do today. The stuff that I'm doing isn't really based on this paper, but this idea isn't novel necessarily, so this paper just describes the same thing. Keyboard can't take it. I don't know. So this is how the keyboard looks. Let's see how the stream latency is. Hey. Alright. I'm hoping it's going to be fine. I mean, it's a new keyboard. It's not a very expensive keyboard, but it's a new keyboard. So let's hope it's all fine. So there's a question in the chat. I'll come back to the chat in a bit because I want to write like a bit of code and actually show something on screen and show some progress, and then we'll answer questions, and then we'll write more code and stuff like that. So I will be ignoring chat for a bit. So last time I started writing some code and then the keyboard broke, but also the other problem was I sort of started writing the wrong code. So today we'll try to write the right code and then see how that works. And basically what we are doing is, so we are trying to say that for each vertices on the seam there is one other vertex in the seam that's after this one. And what I was doing last time was I was trying to build like a doubly linked list, and I realized, and I initially thought I needed a single linked list, and then I convinced myself I need a doubly linked list. And then after the stream on Sunday, I convinced myself that I don't need a doubly linked list, and that I need only a single linked list, and it's slightly easier to build. So today we'll try to build a single linked list, and then maybe we'll convince ourselves that this is not a good idea. I don't know. But yeah, so for each vertex we will be recording the next vertex that is on the same seam. And we will write code that does this, and then we'll write code that shows this, and then we will see how we can use this to like select the right edges. So to be precise, oh, I need to do this thing again. Okay, let me increase the point size again. Hopefully that works. Alright, so that's larger. So all of the vertices that are green are the seam vertices. And you can see that there's like a lot of chains of these vertices that form loops. And this is what we want. We want to have each connection between each green vertex and like the next green vertex on the chain to be represented in our linked list. And so we will do just that. To do that, we need a linked list, and I was doing this last time, but I'll do this again. I basically just discarded all code that we wrote last time because there was not much code and it was also wrong code, so whatever. So we need the next vertex after each vertex in a linked list. So we just need the next pointer. We don't use pointers, we use integers that represent the index of the vertex, because that's faster, smaller, and we like it this way. And you know, people who like pointers can use pointers. We don't like pointers. And the function that we will be filling this data in is going to be classify vertices. This is the function that determines the color of each vertex, or like the kind of each vertex. Is this vertex on a seam, etc. The reason why we will want to do this here is because this is convenient. This function already for each vertex says which other vertices does this vertex connect to, and figures out if there's like the right number of them and stuff like this. So we already should have all of the right information in this function. We just need to record this. So to start with, we'll initialize the linked list to a special value that, you know, if you used pointers, you would use a null pointer, and we will use a special value that is essentially saying, hey, this vertex, the next vertex after this one does not exist. This is if you're not familiar with C++, this is equivalent to this, which is like saying I want the vertex to be -1 because vertex indices are 0 through vertex count -1. But our vertex index is not a signed integer, it's an unsigned integer, so we want to store it in an unsigned integer. And this is like a shorthand. I use it semi-frequently in this code, and a lot of other C++ code bases use this frequently, so that's just like a shorthand. I'm mostly explaining this because some people who are watching this might not be familiar with C++, and this is like a weird thing. Alright. So here we have a few cases that we are enumerating, and we care about two. We care about borders and seams. To go back to, I should just keep it running, shouldn't I? So In this mesh, we only really see the seam vertices, the green ones. There's also blue vertices that represent points where it's on the geometrical border, so there's no triangle on the other side. I talked about this in the last stream. This mesh might not have many. Let's actually see. We should have stats on this somewhere. Aha! So we have this printout here which says how many vertices of which kinds were there in the original mesh. So most vertices are manifold. These are the simple vertices that we don't care about. They're easy to deal with. Border is the vertex on the geometric boundary. So there are some border vertices here. We just can't find any by inspection. I think they might be on the other side of the mesh, because this is like, oh yes, so this is like a person, and we are looking at the back of a person, and in the front there's eyes, and the eyes are these giant spheres that are weirdly tessellated and cut, and yeah, this is where all of the blue vertices are, which means border. And so we have like 2000 seam vertices, which is green, and 200 locked, which is red, which is, we can't do much with them. So only care about border and seam. Now, let's see. Right, yeah, so this should be fine. I think, yeah, this should be fine. So for border vertices, we already have this information in the following form. So let's say this is a triangle, and there's like some other triangles here, but there's no triangle that is opposite to this edge, right? So this edge is a border edge, and these two vertices are the border vertices. So now the way we figure out if the vertex is a border vertex, we look at the vertex and we say how many edges leave this vertex and go to some other vertex. And I covered this a bit last time. There's a bit of a complication. Our vertices are unidirectional, or I mean directed. So they have a direction, right? So, and the direction is either clockwise or counterclockwise, however you want to think about this. Let's say clockwise, which means that there's an edge that goes here and here. And this means that for what we want is like for this vertex, we know this vertex in this code, because we say give us all of the edges that don't have a pair, and if there is exactly one, this means it's this one, right? And this means we say the vertex is a border vertex. So we just need to record the vertex that this edge goes to. This function count open edges has an optional parameter that returns it, so we'll just remember this. We'll call this v, and we'll say we need this vertex, and in this branch we can just record the vertex. I'm wondering if I should, like, if I'm gonna record this value in this fashion, should I just do this in every branch? We'll clean this up later. This code is like slightly asymmetrical, which is weird, but it's a bit easier to write this way because it's harder to forget to fill this value. So let's leave it like this for now and then see how that works. So that's fine. So then the other thing we need is we need to solve this seam problem. And so the seam, like we need to record this information for seams. Oh, actually, should we check if it works for border first? Maybe we should. Okay, let's do this. Let's do this, yes. Okay, let's do this for border first. So here's what we want. I want to like rotate this mesh around, but I don't have rotation code. So let us try to do I have not used OpenGL 1. This is OpenGL 1 in, I want to say 5 years, 5 or 6 years. It's 5 or 6 years when I came to Roblox. Roblox still supported OpenGL 1 through Ogre. and this was not fun. And we've since stopped supporting this, but theoretically there will be some OpenGL voodoo here. Is it GL model view or GL model view matrix? Who knows? It's probably this. And then I think I need load an entity. So let's see if that did something useful. Haha! We rotate the mesh. This mesh looks kind of... Oh my god, okay. That's not great. Okay, fine, whatever. The good news is we have managed to rotate the mesh. The bad news is these. So this is interesting, right? This is how a lot of meshes work. So you see these eyes, and what looks like is happening is these eyes aren't closed. So there is like a boundary in the eye. So the eyeball is cut in half, and the eyeball is embedded into the mesh, and this open boundary is inside the mesh. And we obviously can't see that very well. Let's try to rotate 180 and see what happens. At some point I'll build actual rotation keys into this. Oh, this dude is serious. Yeah, so it's mostly all inside. The reason I want to visualize the edges first on the border vertices is because border vertices are trivial, so like it's easy to make sure I don't mess it up. But okay. Alright, let's scratch that, write seam code, and then write visualization code, and then we might have to debug this code because we don't know if this code works. And I'll keep the rotation code for now because this is useful, because maybe we'll need it in the future. Alright, so seam edges. The reason why seam edges are complicated is because there's like a vertex and there's a pair of a vertex. And then one vertex, and then both vertices are on the seam loop, so one vertex has an edge that goes from the vertex and an edge that comes into the vertex. And the other edge has kind of the same thing. And we are checking these conditions here, but we are not doing a very good job at like recording this data, etc. So we'll need to change a bit of code. So what find wedge edge does, and I went over this last time, is it asks, given a vertex like this that has two copies, is there an edge from any one of these copies to the target vertex? And it just tells us yes or no, right? So we kind of want to return the index of the vertex. But also there's this function find edge that also returns a true or false, and I wanted to fix it for a while. Like, it's weird to call the function find if it just checks if the value is there but doesn't actually give you any location for this value. So let's do this. Let's rename this function to hasEdge, and that's nicer. And then this function will return an index of the vertex. So let's see. So if there's an edge from V to B, and V is a clone of A, so it's one of these vertices that have the same position, then we'll just return V. And if there is no vertex, we'll return this magical thing that's not like -1, but kind of -1. And we're only calling this function in two places, and we'll have to change this if to compare the result of this function to -1, right? So let's do this. So this will be, so this is, we are asking, is there an edge from A to this other vertex? That is the copy of the current one. So let's call this a O. So I sometimes like descriptive variable names, and I sometimes like short variable names. So O I guess is other. I don't know. Let's just call these variables whatever, and then we can refactor this code sometime. And then basically instead of a boolean, this is either -1 if it found it, or if it didn't find it, and then some other vertex value if it did find it. So here we need to say if we did find one vertex and we did find another vertex, then it's a seam. Let's check that we didn't break our code by running our code. Alright, we didn't seem to break our code. So this is good, because now these are the indices that I wanted. So let me try to like display this side by side and draw a picture of this. And maybe drawing a picture will make sure that I can actually write code that works from the first try. That would be nice. So here's what's going on. Can I collapse this thing? Okay, I guess the answer is no. Oh, I can do this. Okay, whatever. All right. So we have a vertex. We have a vertex I. And this branch says the I vertex has 2 copies. Just trust me, the I vertex has 2 copies. And then we say, can you give me the edges that go from I? And can you give me the edges that go from a copy of I to something else, right? And then if there's one edge that goes from I to somewhere, and there's one edge that goes from a copy of I somewhere, so we will call them A and B, right? This is what the function returns. So the assumption is there is an I, and there is an edge that goes to A, and then there is a copy of I that we'll call WI, which is short for wedge I. I didn't really explain the term wedge last time, and I should double check my terminology at some point because some of the terms I'm using are inconsistent. But I believe wedge is a common name for this copy of a vertex that has the same position, so you can think of it as the same vertex and it just provides extra data for this vertex. But it's actually like a different vertex topologically. So if you have a same position in the mesh where there's 2 UV charts that kind of like meet at this vertex, then this vertex has 2 edges. Let's check if this is right. Maybe this is not right. No, this is not the definition that I'm going for. There must be another one. Finite deformation at the vertex of a bimaterial wedge. Alright, whatever. Let's just assume my terminology is right, and then if my terminology is wrong, then one day we'll fix it. So, there's an edge that goes from I to A, and there's an edge that goes from double I to B. And this really should be called something else, because this is like V and this is like W, whatever. So then we say, okay, let's take, and then let's check. Oh, we don't check. Is that right? Oh yes, this is right for a subtle reason, right. So then we say, is there a vertex other than B? And we don't check that it's a vertex other than B and other than A, which is not great. So this can probably happen, but let me assert here that it's not the same vertex, and this might hit in real meshes, and then we'll have to change this condition. But I didn't, this code is not super carefully written, I suppose. So we are asking, is there a copy of B that has an edge, well, first A. Is there a copy of A that has an edge that goes to this WI? And this is what we are calling AO. So we are saying, okay, there is AO that has an edge that goes here. And is there a copy of B that goes back to I? So there is BO that goes here. And it would be amazing if I could like embed this diagram into this code, but I'm not an ASCII artist. So if there is, we say this vertex is on a seam. Awesome. Here's what we want. For the vertex I, we want to say that the next vertex after this is A. For the vertex WI, we want to say that the next vertex after this is B. Oh, and we don't even need AO and BO. Damn it. So we went through all this trouble of changing find wedge edge to return us the vertex, and we don't even need it. That's unfortunate. But we have an assertion. Maybe that's helpful. Alright, to make our code... Oh. Now there, I will not bother changing this for now. So what we are saying is that we know the next vertex for I, which is A, and we know the next vertex for this BI, which is wedge I, which is B. We'd also kind of like to say that we haven't filled this value before, maybe. let's leave this in for now. So let's see if this like dies. Aha, okay. So my assertion was useful, potentially. Hey, I pressed retry. Come on, what? Alright. So I guess this exercise was not in vain. So we found, oh, this is interesting. I guess this could happen though. It's like a weird mesh. I don't know if you wanna call this a seam vertex in this case. So what seems to happen here is that so there's a vertex, so there's an edge from I to A, and then there's an edge from A to the copy of I, so like directly back. Oh yeah, right, yeah, this can totally happen. And this can totally happen. Should we call this a seam? Yeah, I don't see why not. It might be still fine. It might be fine. I don't know. It might be fine. Let's just say it's alright for now. Oh, I should... Alright, we did not crash, which is nice. We did not assert here, which is nice. I will add a to-do here, which is our BO is B. We have a seam that I don't even know how to, I guess, connects both pairs, both vertex pairs to the same target vertex. Does this still mean the vertex can be a seam vertex? And I think the answer is yes, but I don't know. There's like a bunch of to-do comments in this code, and occasionally I go and add one more, and occasionally I go and remove one. And the hope is that the number of to-do comments converges to 0 one day. So here's what I would like to do. I would like to take, so I think we are like done with filling this structure, but there is like 3 parts to this thing. I need to fill this structure with data. I need to use this structure to actually see if I can collapse an edge or not. And I need to change the structure as we collapse edges, and this is like the harder problem. I mean, I'm hoping it will not be too hard. Because when you take an edge, so what's going on here is that hopefully we have a link from this vertex to this one now, and from this to this one. Like in this loop iteration, I described how we fill this link, but this link should be filled on some other iteration of this loop, hopefully. So let's say we decide that we want to collapse this edge, by moving the vertex I to the vertex A, right? What we would have as a result is we would have a direct connection from vertex B0 to A. So if you don't update this structure as we remove edges, we will like stop collapsing these seams after the first edge, which is not nice, right? So if in the event of a collapse like this, we want to update this structure to say, actually, the vertex after B0 used to be I, but I is now A, so it's now A, right? And this is what we have to do. So this is like 3 things that we need to do. And after this, I'm hoping that things will be beautiful and, you know, and stuff. But what I want to do is I want to render these edges to prove to ourselves that our code is not broken. And so this code is like experimental code, right? And I want to maintain a balance between the cleanliness of the code itself and the cleanliness of the interface. So normally if I wanted to pass debugging data out of a function as like part of the function's interface, I would pass something to the function that the function can fill if necessary. But this means that for every change like this, I need to change the interface of my function and change my tests, and it's a pain. So I'm using global variables, and the idea here, as the to-do comment indicates, is that the only purpose of this global variable is to communicate debug only data back to the program that's calling it. This is not thread safe. You should not write this code in your production code, but this is not production code yet. And I will just remove this when like I don't need this anymore, right? Which might be unfortunate if I have to come back to this code like in a few years and add like extra debug visualizations, but this code isn't particularly hard to write, so simplify debug loop. And what we will do is, if you have this variable set, then we will copy data to this function, to this variable, and we will need to do a copy. Let's just do a copy at the end of the function like now. Actually, let's move this copy down as well. So the reason why I want to move, the reason why I want to fill this data at the end of the function is because as we simplify the mesh, we will be modifying this container. And at the end of the function, I kind of want the state at the end of simplification, like what happens after the mesh is ready. And I hope I don't have early returns from this function. I do not have early returns. This is nice. Okay, and now the only thing I need is, oh god, okay, this is painful. All right, so this is why, like, at some point I'll just strip this code out, because debug visualization is like not straightforward sometimes. Oh no, actually this is all fine. Never mind. Okay. So this is all also like to do. This is debug only visualization and will go away at some point. I'm not actually sure if I look at like to do comments in my. This is like a tool that I'm using to develop this algorithm. It's not supposed to be this like permanent solution to any problem. It's a temporary solution to me being able to debug this code and visualize this code. So there's that. So that's fine. All right. All right. This is probably fine. All right. Now I have this code. Oh, okay. Right now I need to do. So now I need a new. All right. Oh, let me just draw this here for now, actually. So I have this code that says, really? Okay. I have this code that says that if you are in special visualization mode, we'll draw like debug points that are colored with the color of the vertex kind. So in the same place, we'll say, hey, I want to draw lines. Line list. It's not line loop. Is it just line? Is it lines? It's lines. OpenGL is weird, right? So there's like GL line and GL lines. How am I supposed to know which enum to use? I'm glad we aren't using OpenGL. Well, we are using OpenGL. We are not using OpenGL 1. I'm glad at some point we will stop using OpenGL. Although, if OpenGL didn't exist, I don't know how I would have written this program. I'd have to use like some framework or some library or something like this, because it's like impossible to write code in Vulkan in this context. This program is 400 lines of code. Almost all of this program is like solving a specific thing that I need to be solving. Like most lines of code here are not boilerplate, they do something. Like they might seem like boilerplate because, you know, we need to load the mesh and we need to build index buffers for the mesh, and then we need to simplify it and we need to record debug data, and we'll need to like center the mesh and stuff. And like these problems seem they're not that important, but you need to solve them, right? So for Vulkan to write this code, you also need like 1500 lines of code that prepare you for actually solving the problem that you have cared to solve. And it's not a big deal in production renderers, because you write 1500 lines of code once and you forget about the thing. But here it would have been a big deal. So anyway, enough rambling, more code writing. So what I want to do is that I want to go through each triangle. For each triangle I want to go through all 3 edges. And for each edge, I want to say give me the edge. This code is technically boilerplate, I suppose. Give me the first vertex of the edge, give me the second vertex of the edge, which is like the first vertex is 0, 1, 2, the second is 1, 2, 0. This could be math. Math is slower. I don't really care, but it's just reflex at this point to write code that's not like slow pathologically. And then I want to check if I didn't need to go through the edges. All right. Let's do more direct thing. So let's go through the vertices. And there is this vertex L that is the next vertex after this one in a loop. And if this vertex exists, we could draw this edge, and we will use the color of the edge that corresponds to the original vertex. And technically the kinds should match, maybe. I want to write an assert here that says that... Is this assert true? This assert is not true. Never mind. Assertions are like a mixed blessing, because you write an assertion without thinking too deeply about the problem, and then you realize that this is not actually true, and then maybe the code works and maybe the code doesn't, and then you have to fix your assertions. Also, I apologize if the noise, there's like a street, and there's vehicles that go down the street, and the street is not a particularly noisy one, but some of the vehicles are. So if there is noise outside, it's not my fault technically, but I apologize for it anyway. So what we want to do is we want to have a vertex v0 that is the vertex that we're looking at, and v1 which is the next one, and then oh wow, okay, we'll copy this beautiful GL color statement. And we don't care about this data. Oh, this data should not even be there. Okay, that's fine. So then we need the kind, which is the kind of the first vertex. We don't need this. We don't really need the if statement. So there's GL color, and then we need to render one vertex, and then the second one. All right. I don't know. Let's see if this works. So what I'm expecting to see is I'm expecting to see green lines between the green vertices. Also I'm expecting, okay. Ha! The code worked! Alright. So this is nice. So the attentive people might notice that there is no green lines like here. There is a good reason for this, maybe. Or maybe not. There is a good reason, at least, for the absence of one line. I'm less sure. Oh yeah, these edges go in the same direction. I kind of expected there to be a gap here, but not on like both sides. So that's slightly odd. Why did I expect there to be a gap? Right, because, okay. Okay, minor details. Let's not bother with this for now. This might be unexpected, this might be fine. I'm not, also, yeah, wireframe mode is not very useful because it hides everything now. I am not 100% sure if this is right. It might be right. It also might not be right. Like, I would think that this vertex should have a link to this one. Maybe. This one is locked. So then we look at the next vertex. Yeah, I kind of expected this to have that. And then All right, so I'm not sure this is entirely correct, but I'm not sure we care. So here's why we might not care, for now at least, right? So these vertices, this is the situation that I was drawing like on last stream where there is a T-junction. Let me, this is the picture, right? There's the T-junction, there's like 3 seam loops. It's horrible, we can't deal with this. So this vertex that's black here, this is like red here. The red color doesn't show through. This is because GL points and lines are horrible. But maybe if we draw lines first and then points, and maybe they become less horrible? I don't know. Let's test this theory. So that vertex is locked, which means it's not movable. Oh, let me also disable. This might make this better. I'm like not, this is not an OpenGL stream, so I'm not explaining the OpenGL stuff that I'm doing, sorry. And also you should not be using OpenGL these days, so what's the point? Alright, this didn't really make it better. Whatever, so you can kind of see this vertex is red. Maybe if these, oh, what? What? My OpenGL program broke. No. No. What? I really don't want to be debugging OpenGL code. Alright, whatever. I don't know. We are not debugging this program, we are debugging the other program. So the point is, this vertex is locked. This locked vertex means we cannot move it. If we aren't moving the vertex, we don't really care about the connectivity structures there because we aren't going to look at them. Now, I do have a plan to be able to have better like behavior around locked vertices. There's a to-do comment somewhere. Not this one. Not this one. So there's this to-do comments, and here we need to write. To make these work, we might need to like compute loop metadata for them somehow. And it's the same here really, I think. But the good news is these are not allowed right now because I was afraid to deal with them. So I'm still afraid to deal with them, and now I will be more afraid to deal with them. Alright, so the short story is we have computed something. This something looks like it's right, possibly, or maybe not, but it's close. Now we need to use this something to do edge collapses. And what would happen if I did like this? Oh, right, because it's not looking. So this is how we can tell. So this is interesting, right? This is how we can tell that our algorithm right now just does not modify this data at all. Because you see, so I'm simplifying the mesh, and you see these contours on vertices that don't exist in the original mesh. This means that the metadata for this loop stuff still has edges that don't exist anymore. And we need to fix that. And then we will be able to just use this data to say this edge is okay to collapse, this isn't. Why don't we do this fix up first, actually? This is nice because this will just allow us to debug like visualization, get it right, and then use this data for collapses. I will take a brief pause to read the chat, to answer questions and stuff. Oh, people say there's a problem with the mic. Is there still a problem with the mic? I can lower the levels. This is interesting because I haven't really, I don't think I fixed, changed. I should have read the chat earlier. I'm also a noob at OBS, so I don't know how to know if the mic is speaking. Alright. Oh, it's speaking very badly. I should have read the chat earlier. Alright. Can I make the chat bigger? Let's see. I mean, I can pop it out. I can listen to my own stream, but then it'll echo. I mean, I technically have headphones, but Then will still echo. It'll be weird. But oh, I see. I can temporarily. This will take some effort. I'm not sure why nothing changed with the mic. Oh, maybe this changed? I don't think so. All right. Is this too quiet, or is it speaking, or what? Does this sound all right? Have I ever checked out? Right. Yeah. If it goes to red, it's speaking. It goes slightly to red now, but. Have I checked out Polygon Cruncher by MooTools? Still picking. What about now? I guess I need to remember to do this before the stream. Because like last time, it's interesting, last time people said that it's a bit too quiet. And I forgot if I changed anything. Maybe I'm just speaking louder. Even lower. Even lower. Okay. Oh, maybe it shouldn't even go. Alright. Maybe it shouldn't even go into yellow zone. Maybe like it should go right between green and yellow. Is that better? Let me Google Polygon Cruncher while. I don't think I've seen that. Right, so this is kind of, I mean, I haven't seen Polygon Cruncher, but that's kind of what I was talking about, I think, last stream. All right. Different gain setting. This is like too advanced, man. I cannot do that. Maybe it's advanced audio properties. Oh, is this the problem? No, this cannot be the problem. This doesn't show. Okay. Yeah, like I don't think I changed anything. This is like really low now. I mean, maybe it's fine. All right. I'm kind of shocked because I did this stream last time from like I moved the mic. I rotated the mic. Well, I guess maybe, right, maybe it's substantially different now. I rotated the mic a bit. All right, so Polygon Cruncher. I have not seen it. I mean, it's like a trial thing or something. But yeah, so this is kind of what I was talking about yesterday, not yesterday, on Friday, where I think there are like good tools for. Oh, there is an SDK. There are good tools in various like utility libraries and whatever. Sorry, what am I even saying? There are good tools in CAD packages, right? So there's like good tools in Blender and stuff. And they might be good. So this looks like it's a proprietary thing that you can get an SDK for. There's a demo and there's licensing information. And you can like pay them money, I guess. Oh, and they can perform the integration process if you need it. So that's like if you have a lot of money. So this might be a good. I think it would be interesting to see how it works on the meshes that I'm like trying to simplify, right? Because this might be a good library as well. Because Autodesk uses it. Oh, as a Pro Optimizer modifier. Okay. So this might work well. Now it might be slow, and I have speed constraints. It is closed source, obviously, but at some point I should really look at Polygon Cruncher and maybe something else to have like a solid benchmark for quality. Aha, now it's quiet and it is speaking. All right. So we are getting to the bottom of the problem, maybe or maybe not. What did I change since last time? This is really odd. This is here. Of course, this is not here. Why would it be here? Okay. It's interesting that, well, this kind of, yeah, this shows. This is like the exact same setup that I had. This is okay. Let's do this. I mean, I could reduce the levels, but the hell. Okay. Let's try to do this. All right. This will be weird. No, I mean, this shouldn't make anything better. Why can't technology just work? All right. I don't even see specific gain settings here. It's just this pretty much. I mean, does this even work? Alright. Damn it. Why can't things work? I don't understand how it worked last time, because... Alright, is this any different? Doesn't have a boost slider. Start a Patreon, will buy you a better microphone. I have a well, I might have a better microphone. I will try maybe streaming from... Okay, I mean, I just moved it further. Let's try to... Yeah, I don't know what to do with this. We might want to try to just do this. Let me... I'll take the suggestion, I'll listen to my own stream. I want to kind of figure out how bad it is. And now I can... Oh my god, this is like really bad. Exactly, it's the distance between mic and face. This is what I'm using right now. Oh no, stop. Okay, I think I will not change anything because as far as I can tell, I just listened to my stream. It seems to be okay, as far as I can tell. I don't know. Unless it just used a different... No, it couldn't have used a different mic. Let me test. Was it just getting data from this thing? Yes, it's still using this mic that I have on desk. I don't know what else to do. So yeah, it's serviceable right now. I don't know. Next time I will try streaming from Snowball or whatever. I can't put it across stream. Snowball, is that? So I had this mic. I didn't. All right. Alright, let's just roll with this. I don't want to spend like half an hour to try to figure this out. I did my best. I will try a different mic next time. Maybe this is the difference between... It's weird that we didn't have problems last time. Anyway, whatever. So, what's the latest with the cluster cone calling stuff? I mean, I don't really have updates on this. I was looking into this at some point, like months ago, and then I kind of shelved this a bit, and I was planning to look into this more, but I've been distracted by a bunch of other stuff. So no updates yet. It's just GL model view, yeah, whatever it works, whatever it was. I forgot what it's... What did I end up with? No, yeah, gel model view matrix. I don't know what. Maybe both work. I don't know. Let's see. Oh. Oh. Alright. Yes, you're right. It is just gel model view. Probably gel model view matrix doesn't work, and it just defaults to the right thing. Or it doesn't even matter what it defaults to. Alright, let us continue and hope the mic stuff is okay. I'm still puzzled. Like, I listened to the stream I recorded on Sunday, and it seemed good. And I don't think I changed any equipment or any settings or anything really. So I am confused. Maybe like if I reboot Windows, but we will not reboot Windows. But maybe if I reboot Windows, things fix themselves. Right, so as I was saying, we have recorded the information about the seam edges. But we are not changing this information as we remove edges from the mesh. So what we are dealing with here is that there's like a bunch of edges that are kind of left over from the old data, and that is not cool. So we need to fix this, and the way we need to fix this is as follows, I think. Keep in mind I haven't like written this code before, so who knows if what I'm writing is correct. So here's the edge that we are collapsing, and for the sake of the argument, let's say that we have this loop thing that's like the next vertex on the edge. And let's say it points this way, right? And then there is some other edge that this guy points to. And this should be the structure. And then there's this, and then this. And so let's say we are removing this edge, right? Now there's like two directions how we can remove this edge. We can remove this edge this way or this way, and these are different. So let's call this A and B. Now so initially we have, let's call, okay, A, B, it's kind of weird. Okay, let's C, D. So what we have initially is loop C is A, loop A is B, and then loop B is D. Now, if we collapse A towards B, so if we collapse the edge in like this direction, right, then A and B get merged and result in B. So instead of this, how do I, okay, let's do this. Let's move this here. So this will be case number 1 and this will be case number 2. So for case number 1, the next vertex, there's no A anymore. And the way my system works is that if you collapse A towards B, then the vertex A disappears, right? I mean, you can say that the vertex B disappears, but vertex A moves towards it, but like this is not how the algorithm works. The algorithm kills the vertex A, and then the edge between C and A becomes the edge between C and B. So this is what we need to do. So we need to say that loop C is now B, right? Now the next vertex after A, the one that was B, it's kind of unimportant in the sense that we just killed the vertex. But for consistency, we'll say that we need to clear it, set it to -1. And then B doesn't change, so this is all good. So in this case, we are killing the vertex B, and we are moving instead of the edge between A and B, there's now an edge between A and D, right? So the next vertex after C is also A. A is still intact. The next vertex after A becomes D. The next vertex after B becomes, oh no, what did it do? Becomes -1, or yeah, let's draw this nicely so that it's clear that it's 1. And this is what we have to do. So whichever vertex we kill, the next vertex after this becomes -1, just to make sure that we don't have like bugs in our visualization code later or whatever. And then we change some other vertex. So the case number 2 is slightly easier, because if we are removing the edge between A and B, then we need to modify both vertices on this edge, right? So the case number 1 is slightly trickier. See, we need to modify the vertex that was there before A. The vertex that had A as the next one needs to have B as the next one. And you know, the issue is this is why I wanted a double linked list originally. We aren't tracking vertices in the opposite direction, so you can only like move along the list in one direction. And I know it's called a loop, and in the ideal case it is a loop, so you can get like to the beginning when you just go forward. But this is not always like this. So have no fear though, I have a plan. Here's my plan. And let me make sure I remember my plan. Let me make sure I remember my plan. Yeah, I think we are good. All right. So here's how the collapses work. Let me make sure the audio is all right. The audio is not catastrophic. People are not screaming. Yeah, I will try Blue Snowball next time. I thought it was too quiet initially, but maybe I'm wrong and it's actually good, and you can just like make it, I don't know, louder, and then it doesn't peak or clip, or I don't know what the problem is. All right, so here's how the code works. We did not go through this last time, which is fine because we can go through this time. We go through a bunch of edges, and then we say, here's the edge that we need to collapse, to kill. The collapse structure has just two vertices in the edge, all right, and the error. And this might feel weird. There is a really good reason why this is done this way. I will not go over this. So we collapse V0 towards V1. So this is like A, and this is like B from my earlier drawing. So then we have a few conditions that say we should not collapse this vertex yet. This is where we will be checking if we want to use this edge or not. And then we modify some stuff, and there's some to-do comments and whatever. But here's the important part. We fill two vectors. One of them says something happened to this vertex. This means either we collapsed the vertex towards some other one, or some other one towards this. And the second thing that we do is that we fill this remap structure, collapse remap, to say instead of this vertex, there is now this other one. So in this case, if we collapse, let's just make more space here. So I was like saying on last stream how one node is not great at some things, but there are some things that it is great at. Like this is really nice to be able to edit things like that. So, so in this case, we are saying that the collapse remap of A will be B. This means we have collapsed A onto B. And in this case, we are saying collapsed remap B will be A. So this basically means if you have a vertex and you want to know where the vertex went, you ask collapse remap. And if collapse remap says it went there, then it went there. Oh, this collapsed lock isn't even important. Alright, I was explaining locked. Log does not matter. Right. If the vertex did not move, then collapse remap of I is I, right? So if the vertex didn't move, then it kind of moved to itself. And so then there's this function remap index buffer that says, here's a bunch of triangles. Let's compute a new set of triangles. And this is really simple. It just says, here's 3 indices of a triangle. Each one goes to this other vertex. And then check if the triangle is not redundant, is not degenerate. And then this is our new one. So I think we can write a function like this. And we'll call it remap edge loops. And we will pass it loop collapse. I suppose the count of vertices would be nice. This might be it. I don't know. So we are filling this, and we have these many vertices, and then we have. I'm trying to be so like you see this code is split into functions. And this is really useful for profiling. I mean, also for understanding the code, I suppose, but for profiling as well. And we'll try to maybe do that if our code actually works. Or maybe we won't have time. We might not have time. We'll see. But I'm trying to be consistent about how I name variables in like different functions, so that if a variable is called collapse remap in one function, it's collapse remap in another function, because this makes it easier to remember. Like this makes it easier to, you just need to associate the name with the concept. You don't need to track down its use and whatever, right? So that's, all right. So here's what we want to do here. So we want to just go through like all vertices. I can't type, why can't I type a plus? Oh, okay. So yeah, my muscle memory is like tiny bit off with the new keyboard. Like with every new keyboard, you have to adjust, you know, the finger position and whatever, and like get used to it over time. So I'm slightly not used to this keyboard, so I'm pressing minus instead of plus. Right. So here's what we want to say. So there's this vertex A. Well, there's this vertex R, which is the remapped vertex. Now, what do we want to say? All right. Okay. Yeah. Okay. It's all fine. Right. So if we moved the vertex that we are looking at somewhere, then we know essentially A, and I might remove these variables later, but essentially we are saying vertex A moved to vertex B, right? Due to how our edge collapse rules work, if this was a seam edge, this means either B is after A or A is after B, right? So if loop A is B or loop B is A, oh, actually we don't even need to be that granular. Maybe we don't need to be that granular. All right, so here's what we want to say. I'm kind of struggling with this. I'll need to remap the targets and the sources, and this is painful. Oh, should I just Huh. I need a moment to think about this. Yeah, like, so these cases are asymmetrical in a weird way. So I need to check. I do need to check what's going on, I think. Or maybe not. Wait, maybe I'm imagining this. So if I just remap the result of the loop, this gets me from A to B. So it fixes C. And then if the source vertex has remapped, then I need to copy this value someplace else. Is that right? So in this case A is dead and this is fine. So in this case A used to be B. This case is complicated. So the next one after B is A, and yeah, I think we kind of need to check this. It would be nice to not have to check this, but I almost feel like we need to explicitly check the edge, which is not great because so why does this not work? So we say, oh yeah, okay, all right. Okay, fine. Yeah, okay, I will write some code. I don't know if this code will work, but I will write some code, and then we will see if it works by running it and then seeing if it works. So here's what I want to do. I don't want to deal with this problem. I want to say that the first thing that we want to do is that we will say that we will change all of the next pointers to whatever vertex they went to. So in here we are saying loop, like the next one after C used to be A and it's now B, if A collapsed to B. So the way to do this is to say the one after C is now the vertex that the one after C went to, which is just the lookup in this map. So let's just say that this is, and maybe this like breaks down in a horrible fashion, and I suspect it might, but let's just try to see if it works. So that's my first step. What this does, so if I cannot do this if, I can only do this if this vertex is not, like if it goes to ether, like if the next one after this one is dead, then it's the same thing, it's dead. So if it's a valid vertex, then we see where it went. So that's the first step. So this should remap, in this case, it should remap the, like it should say the vertex after C was A, now it's B. This was this case that was harder to deal with, I guess, supposedly. And then it will not touch anything else because no other vertex went anywhere. So we will have covered, let's switch to a happier color. So this will be good, like we have done this. We still have these -1s to fill, but -1s are easy. The more important thing is that we need to fill this. So in this case, what happens is that, oh hey, I can make this smaller. It might be easier to read if it's smaller. So here's what happens in this case number 2. We have collapsed vertex B towards A. And the vertex after A was B, but now we've like removed it, and basically we haven't like fixed anything, right? What we need to do is we need to say that in this case, should we just, this feels weird. Oh, and this is where we need, okay, alright, alright, I think we are kind of there. Okay, so let's just say that A is I and B is loop I. Now, if alright, let's just, okay. So let's just do the thing I wanted to do before. So we are saying that if the line of code that we wrote works for the case where the vertices collapse to the same direction where like the edge goes. So we need to check for the opposite case because that's a special case. So basically what happens if B, which is the next one, collapse towards A. So this is the special case when the seam edge is collapsed in a direction opposite to where loop goes. And otherwise I think we can just do this, and then we'll have to clean up -1s later. So in this case we are saying B collapsed towards A. This means that we have to do a slightly weird thing where B doesn't matter anymore, like there is no B anymore. But the next one after A is whatever vertex was after B. That's like removal from a singly linked list, I suppose. So we have to say that the loop A, wait, am I doing this right? Hold on. Oh, this is nice. Okay, never mind. So this is fine actually. And I mean, maybe I should be more consistent here, but I want to remove the variable A anyway. But this is kind of what this code boils down to, I think. So okay, so we are saying, let's do this again. So we are saying there is A and there is B, and B goes after A. If we collapse the B towards A, then this is like a weird condition where the next one after A is whatever was the next one after B, which is this. Otherwise, we are just saying the edge was collapsed. The edge might not even have been collapsed, and we are just saying that whatever the next one after A was, okay, I think this works. All right. And then the other thing that I want to do is, so if the vertex disappears, like if A was the vertex that we were collapsing in the first place, then we want to fill in -1s. And I want to do this like separately, and I'll look into maybe how I can simplify this code later, but so if collapse remap I is not equal to I, this means we killed I, there's no I anymore. So let's just set this to, so I think this might work. I don't know, let's see. I'm kind of tired of thinking if this code works, and I want to just run the code. Did this code work? I guess, so I think this might have worked, right? Like we aren't seeing this weird, like, rounded things anymore. We seem to have an appropriate number of edges now. So the problem is that we aren't only collapsing these vertices alongside these like correct edges. So maybe this is why we are seeing gaps in this visualization where I wouldn't expect gaps necessarily. But I don't know, maybe this code works. Or maybe I didn't think through some special case or some less special case. So I don't know. Alright, whatever. Let's just, I wanna just have this code run and work, and let's just see. So what I want to do is I want to go to the function that picks the edges to collapse. And I want to say, so this function already has like a few checks. And I want to say if vertex kind is so if it's like a border vertex or a seam vertex, and I don't really need that many braces, then either A, so this is the, so we're saying if both vertices are of the same type, which is the only supported case right now in this special condition, and if it's a border or seam, then we want to say see is it true that either A is after B or B is after A in this list? So like, are they connected, right? And the way we do this, oh, and we need like a loop thing here. Ah, come on. All right. So yeah. So if one vertex is not after the other, and the other vertex is not after the first one, then this means that two vertices are on a border or a seam, but there is no direct edge between them. This indicates that they belong to two different edge loops, and we should not collapse this edge, because that would be bad. And if my code doesn't work right now, I'll have to debug this, and this will be painful, and you know, and if my code does work, then we are done. Okay. All right. Hey, this was not for nothing. Oh, never mind. I didn't simplify anything. All right, my code still works. The fact that this edge is missing here is like weird. I'm not sure why that is. Maybe so the mesh looks beautifully clean now, right? All right, I am happy with this. Let us compare the results. Here's what happens when you don't do all of this crazy stuff. And we'll also check the number of polygons. So we have at the max level that this code currently simplifies down towards, we have 1400 verts. And we see this weird stuff that happens, right, where, you know, we didn't do the right job, we didn't do a good job doing the right thing, or whatever. And this is what happens when we do run this code. All right. We have 1400, I think we have one fewer triangle. This does not matter. What does matter is that these results are clean. Let me... Alright, I mean, I guess, like, it's kind of obvious, right? I think this code works. So the only reason why I say I think this code works and not this code definitely works is because the fact that, oh, is this just like OpenGL? Like, this is weird, right? Like these gaps in these edges, they bother me a bit, right? I mean, like, I don't know if they should be here. I would hope that they aren't here. But is it just that I don't see the lines because like the mesh is in the way or something like this? And somehow this doesn't always happen because of precision issues? I mean, I didn't think it should happen, but maybe it should. I'm not sure. Let's see. Basically what I want to do is I want to push out. I want to have like an offset, like a Z bias, and it should be like a small floating point value or something. And then I want to push, and then I want to figure out which direction Z goes. I never know that. I mean, it should be basically negative is towards camera, I think, because this is like OpenGL projective space. So I want to say that I need to do this here, and I might as well do like this here, and maybe I have to flip plus and minus, and it, you know. All right. Ha! My code works. It's OpenGL that doesn't. My code works. Well, I mean, maybe. I mean, there's still like. I mean, my Z bias isn't big enough, right? Okay. OpenGL, why? I mean, it's technically sort of makes sense. Like I'm rendering a triangle in solid mode, right? And then I'm rendering a line that's exactly between one point of the triangle and another point of the triangle. And like you would think that the rasterization rules guarantee you that the line has the exact same Z values that the triangle does. But in reality, it doesn't really work out like this. So why is like this still missing? And also, what's this? Oh, this could be like an internal edge. This is like impossible. Okay, I feel like I'm fighting with OpenGL at this point, which, you know, isn't a productive use of my time. I mean, I don't know. I want to say that my code works. Visualization results are slightly strange, but I think this is just visualization. Yeah, I don't know. I feel like it works. Let me do one more test, which is I want to test on one more mesh. And then I will run the test program to go over all meshes that I have in my collection of meshes, just to see if it like asserts or something, right? Or crashes. This is my collection of meshes. Oh, it's kind of small. Did I like shrink it? Oh yeah, I removed a bunch of useless meshes, I think. How do I do the? Is that how I do this? Right, so it's like 4 GB of object files, so it'll take, you know, a couple of minutes or something, I don't know. But I want to first see a couple of other meshes with UV splits, like does this work, right? So this might not work. Well, right, so this mesh was a complicated mesh where I didn't tune the thresholds right. Like it might not be worse than it was, it might just be not good. Oh, you know what we should do? Let me look at the chat first. Let me look at the chat. The starting curly bracket isn't on the same line the block is starting on. Oh yeah, of course it's not. This is not like KNR C brackets. I don't like KNR brackets. I'm gonna break the keyboard. I'm not gonna break the keyboard. Well, I mean, I might break the keyboard. All right. So, what was it? Oh, let's add a button. We are doing. So I wanted this to be like a 2-hour stream, and it looks like our code works. I don't know if we need to do code cleanup, but let me. So I mean, like, yeah. So this function is slightly edgy. Okay, pun not intended. This function is slightly edgy. It's not like it might be right. It might like work, as in it might be that this function handles every possible corner case that I did not think of while writing code on stream. and it also might not work. Like there might be cases where it's just broken, and it's kind of hard to validate this well. So maybe I want to do, but like the code is fine, right? I don't know. I don't think there's like big issues. We added debug loops, but debug loop visualization. But this is good because I want to like have this code here for a while to be able to debug this stuff visually. So what I want to do is I want to okay, alright, so let's do this. So I want to add a comment that says like audit this code after the stream. You know, audit this code. I think it works because I think this problem was actually like kind of simple, but maybe it doesn't. Can we fold this loop into the previous? Well, yeah. I think the answer here is no. I can just remove this comment before I write it. So this is fine. I don't even know if I need to like, I don't know, this feels like the right solution to this problem. I need to do this thing separately, which is not great because it will be slow, sort of, but it's not too bad. So the only thing, so I want to like commit this code. I don't know. I want to commit this code. Oh, maybe I should run my test suite. It's not that, yeah, okay. This code seems to work. I have like a command line thing that just generates a bunch of LEDs, makes sure that the meshes aren't too badly broken. So this is fine. So let me look at diffs first. Like before, every time when I do a commit, I look at the git diff before doing that, because maybe there's like printfs that I left there, or maybe there's some other stuff that's bad, or God knows what happens. Or maybe I added a tab instead of a space, God forbid. This is slightly, the code style here is slightly weird because like there's no braces here and there's braces here, and this is a bit of a mess. But I don't want to fix it right now. And this is fine, and there's this to do comment, and this is good, and this is our magical condition. And this is beautiful, and this function needs to be refactored a bit at some point, but I think it's fine for now, and this might just be good. So let's commit the source separately. I don't know what else to say there. I could write that the code might not work in all cases because I just wrote it, but I usually don't do that. So now let's commit this thing. I like to prefix my commit messages with like an area of code that I worked on, so that when you look at a giant list of commits in Git, just the first line, just the first part of the first line is good enough to like really quickly tell you, like, I'm looking for changes that touch simplifier. Should I be looking at this change or whatever? It just helps a bit. Load viewer and visualization of edge loops. Also, what did we add as well? There is loops, there is z-bias, but that's like not useful. I mean, it's useful, but I mean, we didn't really do anything else. I don't like single line commits. I should write one more line here. What should the line be? Oh, add draft code for rotating the mesh. Alright. It's kind of redundant, but whatever. It's like a weird style thing. Alright, so quick thing. I want to like hack a key to this magical, beautiful condition and just toggle this and see that it works, how it works on like this pirate thing. And then we will run the tests and I will just answer questions on random topics for like 10 minutes or so, and then we'll end the stream. And then I can go get myself a slice of pie or something, because I feel like I deserve the slice of pie, and I think that place is still open. Yeah, the place is still open. So use magic. We will not commit this code. This code is like really weird to commit. I don't like weird code, but this code is helpful because this will let me quickly test what the impact of this change is on a couple of meshes. I sometimes do this. Like long term, I think what I need to do is I need to just pass a bunch of like flags to this function. Like it might be reasonable for you to basically say, hey, I want the optimizer to just ignore all of these like conditions that try to make the output be better, and just like go with like whatever rules, right? So maybe it's useful to toggle this, maybe it's not. Let's hook this to Q, because Q is the first, you know, button that came to my mind, and then let's just see if this works. Or like, I mean, I know it works, but so this might not really improve much. I don't know. Let's see. Is this changing? Oh, sorry. Wait, this is not enough. Damn it. Damn it. Okay. Okay, whatever. Like the issue is I need to. Nah, okay, doesn't matter. Let's see. Oh, this is amazing. Ha! Alright, so this does work. Okay, so this is the results of my old code, right? Use magic is false. I'm not doing the magic thing. You can see this is the exact problem that I talked about on the stream last time. Like the strip of the UV chart is so thin that my code got really confused and said, hey, it's okay, you can move these vertices, it's gonna be fine, I promise. And then, you know, you look at the belt and it's just not good. And then you enable this condition, you see the rest of the mesh is still like mostly the same. I mean, okay, maybe the head is slightly worse. Is the head worse? Maybe the head is worse. Oh, no, the head might not be worse. The head might be just, this is like, it's fine. It might be fine. It might be fine. Anyway, yeah, okay, all right. So, see, like, the issue here is this interesting problem where, like, so now we are trying to restrict the collapses better. This means that, this means that maybe there's bugs in my code, in my new code, right? But also this means that if you block some collapses, then you are forced to take some other collapses that might distort shape in some other places. So this is why it might be like useful to be able to toggle this code at some point. Wait. There also might be bugs in my code, because this is working slightly more weird than what I would think it should work as. So like this is perfectly fine. How many? Okay, alright, no, maybe this is fine. Like there's so few triangles here to work with that going below like 800 in this case is just really tough. So okay, so I think this might be fine. Okay, let me test one more mesh and then I'll run test suite and then we will do questions or whatever. Do I have like another mesh that's like interesting and useful in this context? There's this like really hard mesh to deal with. This is like a real game mesh. I forgot what company provided it, but it's like an open mesh, like you can use it in research or whatever. And this is tough to deal with. So let's see. Okay, so here we have like the same problem, right? Where it just gets confused and it's like bad. Let's see what. Alright, okay. So basically I think the conclusion is the code seems to work by doing fewer collapses in some of these places. We do a bit more collapses in some other places, which in some cases makes the result better and in some cases the result worse. But that's kind of like at some point I will improve the error metrics and maybe this will all get better. But this is not too bad. I'm like reasonably happy with the result. This was a big deficiency that I wanted to correct. And it wasn't too hard. And now we'll just do this. Nope. Aha. So this just goes to all of my meshes and runs the code on them and wait, what am I doing? Hold on. Maybe I should stop and think. So there's this beautiful code. Let's nuke the beautiful code. Alright, now let's run the test suite. Alright, now I'll read the chat. Oh, there's like a thread on dev forum or something about this. Let's see if there's a thread on dev forum. Alright, this seems to work so far. Oh, I'm not logged in. Can I like log in without typing my password? I have a lot of... Where is this? Is it here somewhere? Alright, whatever. I will not chase this down. Oh, Discord, okay. Alright, that's fine. So I think we're done. We are just running the code to make sure that the code works. I will build the release executable to see what the cost is of the code that we've done today. Or specifically, so performance of this algorithm is kind of important to me. We've added a bit of code to vertex classification, but I think this might not, like, we've added like 2 lines of code to vertex classification, okay, or 4. This is fine. The thing that I'm most worried about is that on large meshes, repeatedly running this routine that remaps edge loops might be semi-expensive, and we will check if this is true. And there are some ways to make it faster in the future, but I just want to see if this is even true. Maybe this is not true. And yeah, if you guys have questions about stuff that I did today, other stuff, whatever, I kind of just can talk for like 10 minutes about whatever, and then we'll end the stream. And then my job for next time is to not screw up the mic. I don't know how that will work, but I will try my best to do something with the mic. This still runs. Oh yeah, this is like a really bad mesh. I have a to-do entry to figure out why this mesh is really slow. It triggers a weird case in my algorithm that makes it really painful to deal with. But this mesh is also insane. Like, do I have this built yet? No, yeah, okay. Like, this mesh is not fun to simplify. This mesh is not even fun to open or render, because it has like 3 million triangles like this. And there's not much you can do with this, honestly. But I'd like my algorithm to not be slow, and it's slow in this mesh. So yeah, questions, comments, complaints, wish lists. I don't know. What do people want to ask about? I do not have a favorite color. I don't know, maybe I should, but I don't have a favorite color. I like all kinds of colors. Let's see. Right, so that's like a complex mesh. It has a million triangles, and it looks like it takes us a couple of seconds. And this is with debug print statements. Maybe if I disable them, it runs faster. To simplify this, let's disable print statements, because maybe they affect our performance unnecessarily. And then we'll run the code through the profiler. We'll see how much time the edge loop remapper thing takes. And then if there's no other questions or no questions or whatever, then we'll just end here, because we did the thing worked. I'm happy with this. Like, the way it usually works is I think I have an idea of how to do a thing, but then the idea is sometimes right and sometimes wrong. Alright, yeah, so without print statements it takes less time. The stream might buffer. Alright. I might have been overloading my system a bit. Alright. So, what was I gonna say? Oh yeah, like when I start doing these things, I have an idea, but my idea may work or may not work. And the only way to know is to try it. And we successfully tried the idea out. I was trying to explain something on stream. Maybe somebody understood something, maybe not. And you know, the idea seems to have worked out. There may be bugs in our code, but we can fix the bugs at some point later. And it seems like this code is not worse. Oh, what? Wow. It's not worse than what we had, sort of, and it seems to be better in the ways that I was hoping for it to be better. So that's good. I am happy with this. Let us look at performance. So this is a C++ profiler, and if we look at just the cost of simplification on this model, alright, so here's the deal. The compiler is helpfully saying that it wants to inline like the random functions that I have in my code, which is helpful for performance in some cases, not in this case. What is it's also not helpful for is it's not helpful for like understanding the results in the profiler at a glance. So this is not great. So we will do this again. Yeah. Like the state of the profilers is kind of sad. So this Visual Studio Profiler is like good for this really high level overview of like, you know, what functions take what time, sort of, kind of, in some cases. But it's not good for a bunch of other stuff. What? So like I removed inlining and the thing got 30% faster? How does that work? Anyway, yeah, and so I tried to install VTune on this system as well, but VTune has some weird problem where I remember last time I installed it on like another laptop that I had, I also had to somehow hack it together up until it actually gave me the information that I cared about. So the state of profilers is kind of sad. It makes me kind of sad as the person who cares about performance. Aha, okay, finally. So remap edge loops takes... Oh, and the other thing is Microsoft profilers used to show these percentages based on like the current view. And now it shows percentages based on the entire program, which is also not great. But effectively, we have over 4309. So we have like 4% of performance taken by this new function, and we might have a tiny bit of cost in classify as well. I'm not sure how large that is. I'm hoping it's not large, but it's impossible to know easily. So I would estimate that we are now like 5% slower or whatever on this mesh, which is fine with me. This is like a really big stress case because we are taking 1 million triangles and then we are simplifying it down to like 1,000. And on every cycle of the simplifier, of which there will be like 20, 30, 40, we are going through the entire array of 1 million vertices and updating this loop stuff. So the fact that it is just 4% is making me reasonably happy. I was like worried that it would be like 10% plus. 5% isn't too bad. There's some other stuff that is also sort of expensive, but this is like not too bad. Like this is like on par with sorting, and I feel really good about my sorting function. So maybe this is not too bad. I will not worry about this for a while. Right, so performance is good, behavior is good, the code might work. Why is inlining bad for performance there? I have no clue. I suspect that maybe this is just noise. Like there are cases where inlining big functions into other big functions is bad because the compiler is getting really confused about the flow of code. Like you have a lot of code that has complicated if statements and stuff, and then you make this code more complex by adding more code to it by inlining, and this can slow things down. But honestly, I suspect that what might be happening is just it's like really large deviations like noise, right? So let's try to see if this actually is reproducible. So with inlining, so this is like 700 milliseconds, right? All right. I'm really 7 to 800. I'm hoping that right now it's also 7 to 800 and then it's just noise and then we can call it a day. But if it's actually visibly slower, okay, it was just noise. It's good. Computers are not a reliable source of timing information when you try to measure performance. Human Dev Forum Discord. All right. Is this going to be implemented into Roblox? I do not know. We will see. I don't think it works well enough so that you can throw, like a lot of my tests are for really high polygon meshes. It doesn't work well enough so that you can throw like a 5,000 triangle mesh into it and simplify it down to 500 and it looks reasonable in all cases. Like you've seen in some cases it significantly deforms the mesh. So it's not good enough yet. One day it might be good enough, or maybe somebody else in Roblox will do something else that's like slower, for example, but is much better quality, and then we won't. I don't have a favorite color. All right. This is not how you use camera block scenes. All right. I don't think there's anything else here. So I will put the recording up on YouTube. It's unfortunate that it seems like that the first like half an hour or so will have clipped audio, but too bad. I will try to fix the mic next time. I don't know what the next stream will be, when the next stream will be, and what the next stream will be. I sort of had a small topic for a stream that's not directly related to the simplifier, but that I kind of wanted to do, which has to do with like STL, and you know, maybe I will. Yeah, there's like basically I was looking at, it was bothering me that the code, this code, in debug mode is kind of slow. And like it's not too bad, but whenever I have to like wait for this thing to load a mesh, it makes me, so this, right? So like I run the thing and then I wait for like 4 seconds, 3 seconds, and then it loads the mesh. And the simplifier is fast, right? This is like debug mode. Sure, it's taking 35,000 triangles and then simplifying down them to like 800, and it's taking like, you know, 200 milliseconds. This is debug mode. This is not optimized code. But to load the mesh, 1, 2, it's like 2+ seconds, 2 to 3 seconds, right? 1, 2, and like it feels weird that to load a mesh you would have to spend substantially more time than to simplify the mesh. And there's a reason for this, and I know the reason, and I might want to do a stream where I talk about this. And this is not directly related to simplification, but this is related to like performance and, you know, C++ and stuff like this. So I thought I might want to do a stream about that. I don't know when I want to do a stream about that. One option is to do this on a weekday. So like maybe we do this in like a couple of days, maybe do this Thursday night. Another option is to do this on the weekend, which would be like Saturday-ish, like early morning Pacific time, stuff like this, like same as last time. I don't know what will happen yet. Oh, this is like a different mesh. Right, okay. Yeah, I should go get the pie, but I feel relatively safe because the pie place closes at 10 and it's like 10 minutes of walking from my place. So if I end the stream in a couple of minutes, I should be good. Right, so okay, like release build, I hit Ctrl F5, instantly I see printouts. When the first line prints here, this is when we have loaded the mesh completely, and this just runs the simplifier in like a dummy mode where it asks it, can you simplify the mesh to the same number of triangles that you had originally? And it just prints diagnostics. So like release build, right? I didn't wait for this, like instantly, boom, boom, done, right? Like debug mode, right? Like how do you go from 2 to 3 seconds of stuff in debug to like a sub-second instantaneous, and we'll have to measure this more precisely. And I know why, and there's not a very good reason. And I kind of, maybe this is what the next stream will be about. Maybe it will be more broadly interesting because it's not just meshes, it's like, hey, C++. Consumed your entire afternoon after work. Sorry, dude. But hey, if it makes you feel better, this consumed my entire afternoon after work. So we are even. Alright, Pylor. Alright, thank you guys for watching. I will, yeah, I'll think about when I want to do, I think it might be Thursday, I don't know, or it might be weekend. I'll think about this. Maybe I'll do a poll on Twitter. Oh, maybe I'll do a poll on Twitter. I will do a poll on Twitter and let the audience decide, and then we'll do a stream about like STL and C++ and stuff. And this is it. And here's more table banks. Alright, thank you guys. See you guys later. The recording will be on YouTube. And I